So we're going to look at the chain rule for a multivariable function. When the function variables are themselves functions of two independent variables. So if we have a function f of xy, and x is a function of two variables s and t, and y is a function of two variables s and t, then to get the total change of f with respect to s, we would need to take the partial derivative of f with respect to x, find out how is f changing because of x, times, and then we need to multiply by how x is changing because of s. So this gives us the change in f versus the change in s because of the change in x. And because f is a function of both x and y, this doesn't give us the entire story for how f is changing with respect to x. So we have to add to the change in f with respect to s, the change in f with respect to x because of y. So we have to calculate partial f partial y times partial f partial s to get the change in f because of s due to changes in the y direction. And then the total change in f over change in s is going to be the sum of the changes. And it would be the same if we wanted to know the partial f partial t. We would get the rate of change of f with respect to x times partial x partial t to get how f is changing with respect to t because of x. And then we'd have to add on the change in f as a result of change in t because of change in y. So partial f partial y times partial y partial t. And these ideas extend to functions of more variables. They also would extend to functions of many more independent variables. So for example, if my function was f of x, y, z instead of x and y, and we knew that z was itself a function of s and t, to get the total change in f with respect to t, we would have to add on the z term. How is f changing because of z times how is z changing because of t, to understand how f is changing because of t in the direction of z, and the total change in f per change in t would be the sum of the changes. So these ideas extend into n-dimensional space, where the n variables are themselves functions of any number of independent variables that you want. So things extend into higher dimensional space and to more independent variables in the way that you think they would. So let's just do one of these instead of two. I don't think that this needs two examples. So let's just say we want to calculate partial f partial s. So I want partial s partial f partial s. I can't write the partial symbol right now. Partial s. So our function f is a function of both x and y. So we know that we're going to need to calculate partial x, partial f, partial x, plus we're going to need to calculate partial f, partial y. But then x is changing because of s, so we need to multiply partial f, partial x by dx ds. And we need to multiply partial f partial y times dy ds. And this will give us the total rate of change of f with respect to s. Right? We're adding up the change because of changes in the x direction plus the change because of changes in the y direction. So we just need to calculate the pieces. Partial f partial x equals, so look at your function, xy squared. So to do the partial derivative with respect to x, we hold y constant. So we look at y squared as being a constant coefficient on x, and a coefficient times x, the derivative will always just be the coefficient. So partial f partial x equals y squared. We can calculate partial f partial y. So when we look at the same function, we're holding x as a constant coefficient on y, so we're going to get 2xy as the partial derivative with respect to y. And then we need to know, what is dx ds? How is x changing because of s? Well, x equals 3s plus t squared, so the derivative of x with respect to s of 3s is just going to be 3, and the derivative of t squared with respect to s, well, t is a constant with respect to s, so the derivative of t squared is 0 with respect to s. So dx ds is just 3, and then we need to calculate dy ds. So we look here, I have y equals s over t, which is the same as 1 over t times s. And because we're taking the derivative with respect to variable s, we treat 1 over t as a constant coefficient on s. So the derivative of y with respect to s is just going to be 1 over t, the coefficient on the s term. And now we can just put those pieces together. Partial f partial x is just y squared times dx ds, so it's times the 3. And then usually you would put the constant in front, so 3y squared would be the more common way to write that, plus partial f partial y, so partial f partial y is just 2xy times dy ds is just 1 over t, so this is over a t right here. And then you typically are going to convert it into from x's and y's into s's and t's. Because we're wanting the partial with respect to s, we would like variable s in the expression. So I'm going to go 3 times y squared, but y is just s over t squared, plus 2 times x, but x is 3s plus t squared, times y, but y is just s over t. And then this was all over t, so there's 2xy all over t. And when I'm looking at this right now, it looks like I have a t squared in the denominator here, and a t times t is t squared in the denominator. So I have a common denominator of t squared, which means I can put the other stuff in the numerator position. So 3 times s squared is 3s squared, plus I have 2 times s times 3s is 6s squared, plus I have 2 times s times t squared is 2st squared. And these are like terms. I can go ahead and combine those. So I get 9s squared plus 2st squared all over a t squared term. I can leave it like this or factor that s and s term off front. I think this is probably good enough right here.